So the series resonant circuit found by the LC and the load. Here we assume that load as the resistive load R. This mode begins when T1 is turned on and the resonant pulse current flows through T1 and the load. Now the instantaneous load current, that is I1 of T. From this circuit we can write that as L di1 by dt plus R is the load I1 flowing through it plus 1 by C integral of I1 dt plus the initial voltage of the capacitor C, that is Vc1 at t equals to 0, which equals to the total voltage Vs. Number 1. We know that the initial condition, that is I1 at t equals to 0 and Vc1 at t equals to 0 equals to minus Vc. The series resonant found by LC and the load must be underdamped, that is, since this is an underdamped case, R square must be less than 4L by C. Let this be equation number 1, then this be 2. The solution for the above equation with the initial conditions, we are going to get I1 of t is equals to A1 e to the power of minus t R by 2L sine omega RT. That is equation number 3. Now where omega R is the resonant frequency, which is given by omega R equals to 1 by LC minus R squared by 4L square under the square root. That will be 4. Now from the initial conditions, the constant A1, when you evaluate, then you are going to buy ID1 by dt at t equals to 0, then you are going to get Vs plus Vc by omega R L, which equals to the constant A1. I1 of t is equals to, with this constant, if you substitute, then you are going to get Vs plus Vc by omega R L e to the power of minus alpha t sine omega R of t. This is equation number 5, where alpha equals to R by 2L. Now we need to find out the equation for the Tm, which is the time taken when I1 of t is max. From the waveform, so you can say that this is half of the T1. Then to find this, di1 by dt is equals to 0, or if you do that with this equation, then you are going to get equation number 6. Omega R e to the power of minus alpha Tm cos omega R Tm minus alpha E minus alpha Tm sine omega R Tm equals to 0. Let this be equation number 7. And this will give us that Tm equals to 1 by omega R tan inverse of omega R by alpha. Let this be equation number 8. The capacitor voltage can be found by Vc1 of t equals to 1 by C integral 0 to t I1 of t minus Vc, which equals to minus Vs plus Vc e power minus alpha t of alpha sine omega RT plus omega R cos omega RT divided by omega R plus Vs. Let it be equation number 9. And this mode is valid for 0 less than T1, where T1 is nothing but pi by omega R. Hence, when I1 of t equals to 0 at time T1. So, at the end of this mode, I1 of t equals to 0 and Vc1 at t equals to T1 equals to Vs plus Vc of e power minus alpha pi by omega R plus Vs. Now, mode 2, when both T1 and T2 are off, let us redefine time starts at t equals to 0, then between 0 time less than T2. The current I2 of T equals to 0 and the voltage across the capacitor during the mode 2 T equals to Vc1, Vc2 at T equals to T2 equals to capital Vc2 that equals to Vc1 as we seen in the waveforms. The voltage at the end of mode 1 is equals to the voltage at the end of mode 2 is same in case of the capacitor. And the current is also 0 at the end of mode 1 and at the end of mode 2 for the output. Now, the mode 3. This mode starts when T2 is fired or on and the reverse resonant current flows through the load. Redefine the origin that T equals to 0 at this point. Then this mode stays between 0, T and T3. Now, the load current we need to find out for this. Then L d I3, since this is the mode 3, I'm substituting I3 by dt plus R I3 plus 1 by C integral I3 dt plus Vc of 3 at t equals to 0 or initial time of the mode 3 equals to 0 since there is no source in the circuit. Now let this be question number 10. Now we have the initial condition that before this the current through this is equals to 0 and the voltage Vc3 at t equals to 0 equals to minus Vc1 which equals to minus Vc2. The solution gives us the I3 of t equals to Vc1 divided by omega RL e to the power of minus alpha t sine omega r of t. Let this be question 11. The capacitor voltage Vc3 of t, will find this by 1 by c integral I3 of t minus Vc1. Then we'll get Vc1 e to the power of minus alpha t of alpha sine omega rt plus omega r cos omega rt divided by omega r. Let this be question number 12. And this mode is valid for, we know that 0 to T3, where T3 is nothing but pi by omega r. At the end of this mode, I3 equals to 0 and in the steady state, Vc of 3 at t equals to T3 equal to Vc3 that equals to Vc that equals to Vc1 e to the power of minus alpha pi by omega r. That is equation number 13. From equation 9 and 13, you can write Vc equals to Vs of 1 plus e to the power of minus z divided by e to the power of z minus e to the power of minus z, which equals to Vs by e to the power of z minus 1. Let it be question number 14. And Vc1 equals to Vs of 1 plus e to the power of z divided by e to the power of z minus e to the power of minus z. That equals to Vs e to the power of z divided by e to the power of z minus 1. Let this be equation number 15. Where z equals to alpha pi by omega r. Now, adding the value of Vc from the equation number 14 to Vs, we are going to get Vs plus Vc equals to Vc1. Let this be equation number 16. The equation number 16 indicates that under steady state conditions, the peak value of positive current from the equation number 5 and the negative current from the equation number 11 through the load are same. Or you can observe from the waveform, the peak value is same. The load current I1 of t must be 0 and T1 must be turned off before T2 is fired. Otherwise, the short circuit condition will result through the thyristors and the supply. Therefore, available off time, that is T2, equals to a turn off available time known as a dead zone. And this must be greater than turn off time of the thyristor TQ. The turn off time, that is pi by omega naught minus pi by omega r, which equals to turn of time greater than TQ. Let it be 17, where omega naught is the frequency of the output voltage and omega r is the resonant frequency. This equation indicates that the maximum possible output frequency is limited by f naught less than equal to f max, where f max is 1 by 2 TQ plus pi by omega r. Let this be equation number 18. This is a simple circuit for resonant inverter. However, the power flow from the DC supply is discontinuous. The DC supply will have a high peak current and would contain harmonics. An improvement of the basic inverter can be made if the inductors are closely coupled as shown here. When T1 is fired, a current T1 begins to rise. The voltage across the L1 will be positive with the polarities as shown in the circuit. Induced voltage on L2 will now add to the voltage of capacitor C in reverse biasing T2, and T2 will be turned off. The result is that the firing of one thyristor will turn off the other even before the load current reaches to 0. The drawback of high pulsed current from the DC supply can be overcome in half bridge configuration as shown here, where L1 equals to L2 and C1 equals to C2, and the power is drawn from the DC source during the both half cycles of the output voltage. One half of the load current is supplied by the capacitor C1 and the another by the capacitor C2. A full bridge inverter as shown in this figure, which allows higher output power. When T1 and T2 are fired, a positive resonant current flows through the load, as well as when T3 and T4 are fired, a negative load current flows. The supply current is continuous but pulsating. The resonance frequency and the available dead zone depends on the load. For this reason, resonant inverters are most suitable for fixed load application. In our case, we consider the load as the resistance R could be connected in parallel with the capacitors. Now I am using SRI to represent series resonant inverter in this video. This is not the standard form. If this video is useful, please like, share and subscribe.